This is a general overview of H2 physics. Okay? Basically, H2 physics can be divided into 5 broad categories. So, the first category that we can have is mechanics. So, the other 4 will be thermal physics, waves and superposition, electromagnetism, and finally, modern physics. Mechanics is a branch of physics that is concerned with the behavior of bodies when they are subjected to forces or displacements. Mechanics here refer to classical mechanics, where we deal with kinematics, dynamics, Newton's laws of motions, momentum, mass, weight, springs, Hooke's law, etc. This branch of physics is usually the first branch that is taught in most JCs. Thermal physics is the study of heat, temperature, energy transfer through heat. Electromagnetism is a study of the interaction between electric fields and magnetic fields, electromagnetic induction, and alternating current. Waves and superposition is the study of waves, means in terms of sound waves, light waves, and superposition is the interference of these waves, how these waves interact with each other. Modern physics is a study of nuclear physics, everything that is modern, everything that is after 1900s. Okay? Specifically quantum physics, nuclear physics, lasers and semiconductors. So for H2 physics, these are the 5 broad categories and they are linked together by this thing called energy. So energy is like the concept that links all these 5 topics together. 1, 2, 3, 4, 5. So with this concept, for mechanics, we have, for example, gravitational potential energy, kinetic energy, elastic potential energy. For thermal physics, heat itself is thermal energy. In electromagnetism, you have energy due to electric fields and magnetic fields. In modern physics, the first chapter is quantum physics, where you learn that light can be wave or particle. So light itself, you'll learn the formula of energy. You'll also learn the energy levels of atoms. In lasers and semiconductors, you learn from lasers how to apply the energy levels of atoms. And finally, for nuclear physics, you'll learn about the energy, the binding energy of different atoms, and how they are related to the stability of the atom. So what is the most important branch for H2 physics? Okay, in my opinion, the most important branch is mechanics. Why? Because to me, I see linkages between thermal to mechanics, electromagnetism to mechanics, modern physics to mechanics, and waves and superposition to mechanics. For waves and superpositions, it's very similar to the topic of oscillations at mechanics. Okay, it's linked. So this itself is a mechanical wave. Here, we learn about light waves and sound waves. In modern physics, we learn about forces and momentum. Forces is where we deal with particular nature of light, okay, where light as a particle can hit a surface, you experience a force which gives us radiation pressure. Okay? There can also be conservation of momentum. So this also applies in nuclear physics. So there's some link with mechanics. You also learn about forces at electromagnetism, how electric charges interact with each other, how a current carrying conductor experience a force in a magnetic field, how a moving charge experience a force in a magnetic field. For a moving charge in a magnetic field is linked to circular motion in mechanics. For a moving charge in an electric field is linked to projectile motion in mechanics. So there's a lot of linkages there. Thermal physics is linked to mechanics in the topic of work done. So work is done when a gas or fluid is compressed. So when a fluid or gas is compressed, usually a gas because liquids cannot be compressed. So when a gas is compressed, there's work done because there's a force and there's a distance moved. Okay? This concludes my very basic overview of H2 physics at A levels. It might be quite hard to truly grasp H2 physics from a short introduction of it in this video, but I hope you can get a very general idea of what can be expected, what is taught, and what is important.